Hello. So we're going to continue talking about forces, but we're going to expand beyond the three forces we've talked about in the past. We've talked about weight, or the force of gravity, downward. We talked about the normal force, the force that's perpendicular to a surface that you're resting against, or an object is resting against, and tension, the force in an object, a push or a pull. For tension, it's usually a pull, like with a rope or a cord. Friction is a very common force, but it's also a bit misunderstood. Friction exists in basically every scenario. It's the reason the ancient Greeks thought that the natural state of objects was at rest. When you push an object, it slows and eventually comes to a stop. The Greeks thought that this was because everything wants to be at rest, but Newton and Galileo found that the reason that this happens is because of an external force, the force of friction on an object. So friction occurs. It is a force that opposes the relative motion of two objects or two systems in contact. It acts parallel to the surfaces in contact. So the normal force was perpendicular to the surface. Friction force is parallel to the surface. Now, it opposes motion. It doesn't like motion. So you have two objects moving along one another. Take your two hands and slide them. Do that fast enough. You can feel the heat that's generated because of the friction between the two surfaces. Now, previously we hadn't worried about friction. We were in problems. We talked about frictionless surfaces. Surfaces that have infinite slippage, where there is no force of friction between those surfaces. That type of a system really doesn't exist. Even examples where we talk about being on ice or being on an oiled floor, those actually still have friction. It's just very, 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 very small amount of friction. The purpose of a lubricant is to reduce the amount of friction, but it really can't eliminate it. So a frictionless surface is really a theoretical construct, but we use examples where friction is very low and doesn't greatly affect the outcome to do our previous examples. Well, now we're going to worry about friction. We're going to consider the effects of friction in a system. Now, friction is broken up into two different types. There's kinetic friction, which occurs when the two objects in contact are moving with respect to one another. So imagine placing a box on the floor and then pushing that box along the floor. The bottom of the box is sliding with respect to the floor. Those two surfaces are moving with respect to one another. Therefore, kinetic friction applies. And we'll talk about the differences in just a moment. If the surfaces are not moving with respect to one another, then we call that static friction. An example would be, imagine a really, really heavy box on the floor. You go up and give it a light push, it doesn't move. Well, in a frictionless case, it would move. You're applying a force. There's nothing that can counter that force. Friction doesn't exist, so that box would slide, regardless of how massive that box was. Now, the acceleration might change depending on the box's mass, of course. A massive, massive box will have a very low acceleration compared to a low mass box. F equals ma after all. However, because friction does exist, when you go up and push a very heavy box, or you push a car, let's imagine you have your car in park, and you go up and you give it a shove, your car doesn't move. The reason it doesn't move is because of static friction. Now, if you're really strong, or you have a lot of friends towing, even though your car's in park, the tires will slide along the ground. Eventually, you can pull hard enough that your car will be dragged without the wheels spinning. Then that becomes a kinetic friction problem. So note that the static friction is when the surfaces are not moving with respect to one another. Kinetic friction is when they are moving with respect to one another, which means that only one of these can apply at any given time. So in my box example, I go up and I shove a heavy box on the floor. It doesn't move. That's a static friction problem. I shove even harder. Eventually the box starts sliding. Then it becomes a kinetic friction problem. Going back to my box analogy, imagine a large box sitting on your kitchen floor, tiled floor or wood floor. You can do carpet as well if you want. but a large heavy box is sitting in the middle of your floor. If you don't go and push on it, there is no frictional force. Remember, frictional force is applied parallel to the surface. Not up or down, but parallel to the surface. So if you don't push on that box in static friction doesn't push back, trying to resist the motion. If you go up and give a very light push on that box, the box still doesn't move, because static friction is lightly pushing back to prevent the box's motion. If you push harder, remember this is a very heavy box, if you push a little harder, it's still not moving. Well, for the net force to be zero, that means, so there's no acceleration, the box's velocity doesn't change, it remains zero. When you push a little bit harder, the box has to push a bit harder back on you. So static friction is actually a variable force. It applies the amount of force necessary to prevent motion. So here we have, as a function of time, a graph of friction. Small f is usually used to represent friction. I believe your book uses that as well. Friction as a function of time. So imagine I go up to that box and I slowly increase the force I apply to that box. Well, the frictional force also slowly increases with time to match my pushing, until I push so hard, eventually the box starts sliding. So there's a maximum force that static friction can push against, and no more. Again, the car analogy, going up to a parked car and pushing it, it's not going to move. But hit it with another car, and that car will definitely slide. Hit it with enough force, and friction can't stop the car from moving. Just like with the box analogy, push it hard enough, eventually the box will start sliding. This breaking point, when the box starts sliding, is the maximum amount of static friction the box can apply. So this is F sub s, comma, max. That is not variable. That depends on the surfaces in contact and the weight or how hard the object is being pushed up by the floor. And we'll talk about that in a moment. Now, after that box starts moving, if you've ever noticed, if you've ever done this, pushed a heavy box, you notice that once it starts sliding, it's actually easier to push. So what happens is the static friction drops a bit and then remains roughly constant. Now here, the box in this point is moving. So you end up with kinetic friction. Here, box is stationary. So this is the realm of static friction. This is the realm of kinetic friction. But unlike static friction, kinetic friction really isn't a variable force. It does wiggle a little bit depending on how the surfaces change. But assuming the surfaces are perfectly uniform, the kinetic friction actually remains roughly constant and is given by this value F sub k for kinetic friction. So the static friction, F sub s, has to be less than or equal to this value mu sub s. This Greek letter mu, mu, is used to represent this coefficient of static friction, sub s because it's static friction, times the normal force. So if you want to know what the frictional force has to be, you need to know what the normal force is on that object. How hard is the surface pushing up on that object? And it kind of makes sense if you think about it, right? You try to push a box, there's static friction. If you lift that box off the floor, that floor is no longer in contact, there can be no more friction. And the normal force is zero from that floor to the box. So static friction is a variable force. It goes from zero, when there's no force pushing on it, up to F of s max. So this value here, F of s max, is equal to mu sub s times the normal force. Now the normal force you'll have to get from the free body diagrams. Maybe it'll be given to you, but you have to create a free body diagram and typically solve for what the normal force is. Once you know what the normal force is, you can multiply that by the coefficient of static friction to find out what the maximum frictional force is for static friction. Now, mu sub s is called the coefficient of static friction. It depends on the surfaces in contact. It's not something that you can derive. It has to be something that's tested. Pushing a box over linoleum floor will be slightly different than pushing a box over a wood floor, or over carpeting, or over concrete, or over a floor that you've sprayed with WD-40 or some other lubricant. Although WD-40 is technically a water displacement, forget that. So some lubricant, some oil, changes that coefficient. So some problems you'll be asked to solve for the coefficient. What is the coefficient between these two surfaces? Other times you'll just be given that number. Now this is static friction. Let's look at kinetic friction. All right, we've changed this to kinetic friction, F sub k. Same plot. The kinetic friction is applied when the box is moving. It's approximately constant. So therefore, the force of kinetic friction is equal to mu sub k times the normal force. Now again, mu is this coefficient of friction. Mu sub k is the coefficient of kinetic friction, as opposed to mu sub s, which is the coefficient of static friction. So mu sub k is also not derived. It has to be experimentally determined. It usually is a bit less than the coefficient of static friction because F sub k is a little bit less than F of s max on this plot. It's a little bit easier to push something when it's moving than to get it moving initially. And n is still the normal force. So you can see that the form of this equation is very much the same or almost identical to the equation for the maximum static frictional force. F of s max is equal to mu sub s times n. F sub k here is equal to mu sub k times n. Again, mu sub k and mu sub s are unitless numbers. There's no units to this coefficient. It's typically a number between 0 and 1, but it can exceed 1 in certain cases. For example, imagine a floor of Velcro trying to push a box with the opposite Velcro on the bottom. It's going to take an incredible amount of force to rip that Velcro to get that box moving and to keep it moving. So mu sub k is typically, it can't be less than 0 because that means effectively it's a frictionless surface. It typically is less than 1, but doesn't have to be. You can come up with unique and creative situations where the coefficient is greater than 1. And this has to be unitless if you think about it, because this is a normal force. It's measured in newtons. This is the force of friction, in this case kinetic friction. It's measured in newtons. So newtons is equal to something times newtons. The only way that works is if mu sub k has no units. So then we end up with newtons on the left-hand side and newtons on the right-hand side.